Hello everyone. We all know that pure math always presents itself as being highly ecological, non-energy consuming, non-polluting, etc. And I suppose applied math in that case and computation is exactly the opposite, so that's why we're here. The perspective that was shown to us a few minutes ago, I'm being wired, so I have to be very careful what I do. The perspective that was presented to us just a few minutes ago about the exponential growth of things, of whatever we may be talking about, has of course several implications in terms of costs and several reasons driving this potentially exponential growth. And one of them is of course energy. Just a few days ago I was talking to some engineering and sales managers at Huawei, and I asked them, in your not your own uses of course, but in your customer pool, in your pool of customers, what is the role of energy and what is the cost of energy at the operational expenditures level? And the answer was 70%. So they were telling me, I don't know how accurate this is or whether this is specific to Huawei, but certainly they were claiming that a lot of the systems management issues which consume human resources are being automated, while what is related to energy consumption is just growing and staying large. Okay, as equipment is being installed to automate things, to make things more efficient and so on, as more communications equipment is installed, even as communications become cloudified, despite all of that, energy remains and is becoming even more a nuisance, the cost of energy. This morning in a conversation after breakfast, we talked about a lab in Southampton. It was pointed out to me that this lab has a consumption, spends 800,000 or 900,000 pounds in electricity per year. And of course we've heard about over the £1 billion of BT's expenditures in energy and so on, electricity. So we know all of that, and my talk will be a flash, kind of a flashlight, pointing to a certain number of activities where this relationship between computation and energy comes out. So that's what you will see. There are 4 more slides and I'll be able to show you, at least seriously. However, I'll try to point to a certain number of areas, and I think you will find that some of these areas actually resonate with your own work. So I'm looking at energy, computation, and communications. I'd like to take a holistic approach. All the slides that you see there are related to some of my work over the years, and some of the projects that have funded this work are listed. There are a couple of more that I haven't put there. Now, the thing that you've seen, I'm certain, from the old 2007 Gartner report was the role of energy in ICT per sector of ICT, simplified sectors of ICT. And what you see on the left-hand side is, if you wish, everyday usage, including in the office and in the lab. And what you see on the right-hand side is down there the data centers, and up there the telecoms. And we have this like 50%, 25%, 25% separation, data centers being a little bit less than 25%. But that's the energy consumption in telecoms. And when you look at the telecoms up there on the right-hand side, you have on the left-hand side everyday usage, data centers, and telecoms. And if you look at the telecoms, of course, you're just seeing the stuff that's up in the air, but the reality is the backbone networks as well. The fiber networks, the backbone networks, the routers, the cloud systems that support that, and so on. Okay, so that's what you're seeing. And despite the years that have gone by since 2007, this general pie chart has not changed too much. And the predictions are not altogether false. Okay, so if you look at the midterm, there was a midterm review of this a few years ago, and basically what we saw was essentially this thing happening This was up to 2012, and I participated in a parliamentary review recently over the last year, and what you see is basically this trend, okay, about approximately a 5% growth in energy consumption. And sometimes the debate is, have you included entertainment? Have you not included entertainment? Have you included games? Have you not included games? And so on. There are a number of areas that go in and out of the pie charts, but this is the kind of thing that you're seeing. So we have a steady growth in energy consumption, despite, of course, the fact that all our equipment, everything, is far more efficient than it used to be 10 years ago, right? And if you look at the electricity consumption worldwide, you see the numbers from China, EU, etc. But what you have to keep in mind is that ICT today is going to be roughly the equivalent, ICT electricity today is going to be roughly the equivalent of Germany plus Japan as a whole. So two major industrial economies, their total electricity consumption is equal to the total electricity consumption of ICT worldwide. Okay, so that's kind of the thing you need to look at. And one talks about the CO2 impact, one always talks about 2% of emissions due to ICT and so on, but of course those depend very much on how we generate electricity and how that evolves. Another thing that you might kind of note for the UK, it's that Hinkley Point is roughly going to cover the equivalent of our ICT consumption in the UK. Okay? So that's the magnitude of the affair. So as we go along, we ask ourselves the obvious question: what can we do to rein in on this phenomenon? What are the kinds of things that we can do to rein in on the phenomenon? One interesting aspect is sharing the infrastructure. So things like data centers they're good. Why? Because we can do a lot of optimization in data centers that we can't do on small equipment. So there's a lot to be done in solidifying, consolidating the infrastructure, sharing the infrastructure. In telecoms, sharing the mobile base stations, doing more of that. It's beginning, it's not happening, but doing more of that is certainly going to be important. Do a lot about not using software just all the time. Move it away if you're not actually using it. Things of that kind. Operating at optimum load, speed, and power. There are all kinds of things we can do in that direction. Doing traffic routing in a sensible manner so that we reduce energy consumption. So I'll try to give you a certain number of examples with measurements and models as we go along. Of course, we are here at this meeting to hopefully looking at radically changing technologies. So revisiting the way we do computation and communication to see whether we can do something about all of this. So let me move on to something very different, neurons and energy, right? So you can think of a neural network and think of the biology, okay? Think of the biology. And in the biology, you can say, well, basically, a neuron, or our neurons, won't operate unless we have energy going down at the right level, at the right spot, etc. And what I read in neuroscience papers is that the synaptic connections in a neuron are the main consumers of energy. Okay, as you know, there are electrical connections, there are chemical connections. In the chemical connections, there's a substantial amount of energy consumption. And one can look at a neural network as a neuron, a neural network, as something where there are points of energy consumption. And a modeling approach can include, trying to do that, can include the effect of energy in neural networks. And as you do that, you can think about small qj as the action potential as it is perceived at the synaptic connection. Okay, so it's the post q sub j. Small q sub j is the postsynaptic action potential. What you're sensing as an action potential at postsynaptic level, and then small epsilon sub j represents the probability that the axon is able to convey this postsynaptic potential through presence of energy, okay? Because you will need energy to go from the soma on down to the axon. Now, EJI, on the other hand, is the probability that energy is available at the dendritic connection level, that you can actually go into the next neuron eye through the dendrites, okay? So then you have QJI is, in a certain sense, the effective action, the probability that the effective action potential from J to I is being conveyed, which includes the fact that you have the postsynaptic action potential, but then you also have the energy to accompany it. Now, if you include that, and then you can say, well, can I also look at the energy needs, the probability that I have energy at the synaptic connections? Do I have energy there in a very minute area, region of the neuron? Do I have energy there to be able to operate, to actually have the synapses trigger, right? And then you're going to have some flow, gamma I, of particles per second, which are the conveyors of energy. They may be ATP, you may actually look at sugar molecules. Anyway, so you're going to have some kind of flow. You can, gamma sub I, you can think of it as either particles per second, or you can think of it as power. Okay, power being conveyed, each particle carrying a certain amount of energy, power being conveyed, and this is the consumption, okay, the total energy consumption at the consumption rate, rather, at the synaptic connection. So this is translated, what I'm showing you there is a translation of neuronal structures into, so as to include also the effect of energy, and then you're going to have state equations that describe how, this is for a fully connected network, you're going to have state equations which include the synaptic weights, okay? But also the effect of energy in the system. So here, in this equation, the assumption is that you have enough energy to action the soma, you have enough energy to action the dendrites, and that you're focusing on the energy available to trigger events at the synaptic connections. So what I'm trying to show you is the presence of energy in neuronal networks, which is, I think, interesting and might also have interactions with other areas such as memristors and so on, or the architectures that our Professor Ferber will be talking about. Now, on the other hand, energy is present everywhere, okay? And it's also present if you look at long-running programs. If you take long-running numerical programs, the ones that run on supercomputers, those programs have to be checkpointed. So you have to introduce checkpoints, because if the execution interrupts at a certain point, you've lost a lot of stuff, and you have to start it all again. So what you do is you checkpoint it. Well, interestingly enough, the way you checkpoint has a huge effect on your energy consumption. Why? Because obviously, if you checkpoint very frequently, you will have a substantial amount of overhead. If you checkpoint very infrequently, then when a failure occurs, you have to do much more work, right? And this also, not only on execution time, it also has an effect on energy consumption. So there you have, I think what you're seeing there is the logarithm of energy consumption up there. This is from some work we're doing in one of our projects, logarithm of energy consumption, and the, if you wish, the number of instructions between checkpoints and gains and so on. So moral of the story, energy is everywhere. It's not just in neurons, it's not just in hardware, it's in the way we do software, the way we organize it, and so on. As we go along, okay, I'm skipping a lot of things. Let me talk a bit about wireless. Wireless is very interesting, okay? When you have a lot of wireless devices, like base stations, operating together in an environment, what happens? They interfere with each other, right? So the natural tendency is to speak louder, to increase your power. Well, actually, doing that indefinitely is a very bad idea, because then your energy consumption goes up, right? So you do have an optimum power level so that your communication is the most possible energy efficient in amount of data forwarded correctly without errors, okay, per energy unit, okay? And this is the point that's being made here. Don't worry about the formulas and the equations and so on. It's an issue of understanding, at the end of the day, what's happening here. So this is the efficiency of the communication in terms of the amount of useful stuff that gets through per energy unit. And what you have here is the power level, okay? So definitely there's an optimum. So definitely speaking louder, as we know, of course, in in conversations, is not the solution. You know the effect of American restaurants, where everyone starts speaking louder and louder and louder, and no one, and still less, hears each other and understand what other people are saying. So that's another interesting effect to keep in mind. Okay. And of course, this has a lot of ramifications also in the way we organize storage, in transmitters, and a number of other things. I'd like to tell you some very simple things about servers. Now, with respect to servers, our ideal server is the one up there where the power, pi, is proportional to the load. Okay, that's an ideal server, no load, no power, high load, higher server, right? Just a linear relationship. Well, let's suppose we have such a device. Okay, now then we can say, well, the energy consumption per job in joules is going to be what? It's going to be the power divided by the number of jobs arriving to the server per unit time, right? So you're going to have that, and lo and behold, you see that this ideal server, what is it doing? It has an energy per job which is directly proportional to the average service time of the job. Okay? So you have this very kind of comfortable thing using elementary queuing theory. Now reality is a bit different, because the real servers always have a power consumption even when they're idle. Okay, they have to remain awake, they have to have an operating system, etc., etc. So there's power consumption even without load, and this might be a kind of just sub-idle but a bit more realistic. So this formula is very simple. So then you have the energy per job, which takes this form, okay? And of course, this formula tells you why we like data centers, why we like to concentrate work, because this part will tend to zero, right? But it's kind of interesting to look at this from a slightly more practical perspective. We did a lot of measurements on energy and so on, and say, well, suppose we set ourselves a cost function which says we'd like to operate our system so that we are setting up a reasonable compromise between response time to jobs and energy per job. Okay, there are these two different things. So A times response time, average response time, B times energy per job. So if you do that, here is your little formula. And as you go forward, you can even do measurements and see that the response time formula more or less fits measurements. If you choose, of course, the average job execution time from empirically, you plug it in. And similarly, if you look at the average energy consumption per job versus load, you have something like that. So you see these two things happening. And then you can show that the optimum operating point, the load at which you should be operating to minimize this cost function, which says I want my to achieve a compromise between the amount of energy that I consume and the response time that I receive for my jobs. If you do that, then you can actually compute the optimum operating point for your system in terms of load. And you can go ahead and compare this with experiments and see that for different parameter sets, different servers, and you can see that the theory agrees quite reasonably well with the math. And then the other question that you have is, fine, now I have these servers, but I don't have one, I have many, and I want to share my work. Suppose you have your some kind of dispatcher of jobs, which may be some handheld device, which is deciding which Google site to look at or which other thing to use, which server to use. So you have a dynamic dispatching of your requests over the set of servers, and your purpose is to achieve a compromise overall over all these servers between the response time and the energy consumption. Okay? So again, you set up your cost function based on queuing theory and based on a very simple, very simplified model of the energy consumption, and you can find a way to share load optimally, which will also depend, as expected, on the speed ratio of the different devices you're using, because the speed ratio is going to affect the speed of the devices, it's going to affect the response times, and so on. And so you're going to have a nice way of looking at optimum sharing of load between many devices. As you go along with these ideas, you can also think about on-off systems, and I'll just show you something which is not nice. On-off systems are good, but they have a problem, and that is that putting systems to sleep and waking them up is energivorous. Okay, so that's the measurement that you're seeing there. Power versus time as a system is resuming, power versus time as a system is hibernating. So every time you switch systems on and off, you're just going to consume energy, and any trade-off that you're going to accomplish in such a system will have to take into consideration the overhead of wasted energy due to putting people to sleep and waking them up, putting computers to sleep and waking them up. Now, lots of things to be said about wired networks. I'll just say these are measurements that we did on routers. They're power consumption measurements as a function of load. So what's interesting is that these characteristics are nonlinear. So the power consumption characteristics of a lot of the routing equipment, you have something nominal on the back which says this is so many watts or so many kilowatts. In fact, don't believe them. The reality is much more complex because it's highly dependent on the load, and furthermore, it is also not linear. Okay, so you have to look at that carefully, and if you do that, then you can come up with routing schemes that share traffic across the network so that you exploit the good power operating points of the various routers you're dealing with, and you can overall reduce the power consumption on average over your nodes at the expense of possibly increasing the response times. So let me just show you something else about networks that you are all familiar with. As you know, internet packets all commit harakiri at some point, right? So what do I mean by that? I mean by that when you send out an internet packet and it's been hanging around the network for too long, it's discarded. So the packet is discarded by the router where it is, and the owner of the packet has a sense that by that time the packet has been discarded. Okay? So suppose we have a network like that, and suppose we're interested in the harakiri time. So you simulate that, and you see that, in fact, the average network traversal time, of packets, depends on how you choose your harakiri interval. Okay? So that time is critical in determining the minimum average traffic traversal time. The idea being that you're better off discarding a packet that's gotten lost because it'll never find its destination. It's just way off, and therefore you should get rid of it, or it was already lost. So for some reason it was already dropped off a router. So you have an optimal value, and these are simulations. Now, if you do the math, you can actually build a diffusion model to represent using diffusion processes. This is stuff out of a paper we published in Physical Review. So you can build diffusion processes, and you can calculate the average time as a function of the deadline that you have set. Okay, the time it takes to destroy the packet. So you can look at that, and you can also look at the amount of energy that's consumed. Okay, because every time the packet moves, there's a router that's going to be doing something for it. There are lines and switches that are going to be carrying it, so that is going to create an energy consumption. So as a result of that, you can also compare what the theory says with the observations you have the experimental observations or the simulations that you do, and you see that these things actually agree quite nicely. And then you can look at other ideas, such as, should we send out several packets at a time, not just one at a time for one thing, but several, and can we hope in that way to reduce energy, etc.? And the answer, actually, strangely enough, is yes. So, so these are a few pointers to. I have 5 minutes exactly, which is good. A few pointers to things where you can look at energy and computation and communication and so on. And there's an idea which is worth exploring a little bit, which I call energy packet networks. What's an energy packet network? It's a system which only dispatches energy somewhere if it is needed or wanted, okay? Don't send, if you have, say, a board with lots of sub-chips and things stuck into it, okay? Suppose you have a smart switch that sends stuff on demand to the various parts of the board, okay? So that you're not consuming energy where it is not needed at that time, or where it can be delayed. So the idea is to do scheduling, if you wish, energy scheduling. And actually some Japanese people have implemented this. There are some 2 or 3 papers from Japan where this idea has been implemented, incidentally, in parallel with my idea. So this happened in parallel, and they had already this idea of implementing this kind of switching, and I had this as a theoretical approach or analytical approach to analyzing such systems and optimizing them. And there are a number of pieces of work related to that. The last thing I'd like to mention is perhaps the only one that's directly related, fully related to the future, okay? And here's the possibility. Suppose we use particles charged with spins, charged particles with spins. So we use the charge to move the particle, and we use the spin as a way to carry binary information. Suppose we do that, can we do something interesting? So of course, the reasons are that we would be dealing with a few electron volts rather than with, say, nanoamps or milliamps. So how can we go down to a much lower level of energy consumption? So I've done a couple of things in that area, and there are a lot of interesting questions which come up, because when you start doing that, what do you have to worry about? Well, you have to worry about noise, so switching, polarity, okay? You have to worry about entanglement, okay? So that, for instance, if 2 particles go together somewhere and one switches, the other will switch, okay? If they are going to different places, if that happens, then you're duplicating error. If they're in the same place, they cancel each other out. If they're headed towards the same destination, they're canceling each other out. But if they end up in different places, then they'll be duplicating error. So you have to look at that. And you also have to look at issues of settling. So the Ising effect, okay, of particles joining each other and joining each other's polarity, being influenced by each other and joining each other's polarity. Now that can be good because it's a way of obtaining majority consensus. Okay, so the majority is correct, therefore I join the majority. It's a way of obtaining majority consensus, but it's also a way where a majority can be formed and blocks the forwarding of any different type of information. So one can analyze this mathematically and obtain some interesting results and compute error rates. Of course, the purpose here, this is some kind of Wheatstone bridge where you're collecting particles of different polarities at the 2 ends of at the 2 inputs, and you are deciding on the, if you wish, polarity of the flow, the net polarity of the flow, and you're looking at the probability, the error probability, and what one can show that if some of the parameters of this bridge match the input rate of particles, then you can clean out, you can tend to eliminate the errors that are introduced. So there are lots of interesting things to be done, and the question, of course, here is what are the minimum particle rates that are needed to be able to operate such a system in a reasonable manner. So let me come to the end and repeat some of the challenges. Okay, we have, of course, a growing infrastructure. I agree with the first speaker who indicated that, well, we'll have more and more things. Now there are vehicles coming along. Don't forget that our body gives 20% of its energy up here. So we can expect, I mean, no one should be totally surprised if in a few years we find out that 20% of electricity is actually consumed in computation and communication, which is kind of a huge amount. So that's where we're headed, perhaps. We need to think carefully about various aspects, how to manage systems carefully, how to also consider what are the optimal equipment replacement policies we should be looking at. Consider a large, this is a problem that no one has actually solved, consider a large park of, say, routers run by an organization. That organization has the following problem. They have to replace, at some point, equipment has to be replaced. Okay? However, you can also do it a bit differently and say, at what time will I replace this equipment so that I have energy savings without a cost increase, or energy savings of a certain level with a minimum cost increase. And it's a kind of a very, very interesting OR problem that perhaps someday someone will look at. All right. I think I will stop there.
If anyone's got any burning questions, we could squeeze in a couple. Does anyone have any questions?
Yeah, so what's wrong with just simply heating our houses with computers?
What is wrong with what?
Heating our houses with them. You know, I have
We do that.
electric heater.
We already do that.
I don't.
I do it in my office.
Yes.
And we have a very poor heating system, so my office is being heated by the computer.
Yes, so that when you say that the energy is being used by computers, it's not. It's being used to heat your office. So your estimate's wrong.
Yeah, right. However, you know, at the other extreme, you have to run a fan.
Well, a heat pump, which would work, isn't it?
Yeah, good. That's certainly a way forward. It's not been done very much, but it could be done, yeah. Yeah. Actually, it's not. I know of a data center in Germany that actually uses the cooling water from the computer center to heat part of the building.
Well, I wanted to heat our university building that way, but they wouldn't let me do it.
You see, that's when you have a good idea, they never let you do it.
This gentleman.
Happens to me all the time.
I'm struck with the fact that even more energy is used in the actual manufacture of the equipment.
Absolutely.
For the running of the equipment.
Absolutely.
I'm sure that's in a sense a bigger problem than the running.
Definitely, but it's all together. Yeah, it's several, you know, it's 4 or 5 times more. Just not just manufacturing, but decommissioning.
Yes.
You're absolutely right. That's why one might think that, for instance, the south of China has an electricity expenditure of the order of 25% or so of the total electricity just for computing, either for manufacturing or operating.
Okay. I'm very conscious that we're going to be running late for tea break, so thank you very much, Erol.